Hello everyone, my name is Brad Stiehl, and today I'll be presenting Scalable Quorum-based Deep Neural Networks with Adversarial Learning for Automated Lung Lobe Segmentation in Fast Helical Free-Breathing CTs. Lobe segmentation is one of the tasks required to simulate and plan surgical lung procedures and perform biomechanical property estimation. However, it is impractical to perform even semi-automatically for the number of images that we propose to use. An accurate segmentation of the lung lobes is critical to these proposed workflows. Current approaches use breath-hold CT images and algorithms that identify vessels and lobe fissures and couple them with lobe-shaped models. While some of these algorithms are automatic, they have been observed to produce inaccurate results due to patient anatomy variation. Furthermore, many COPD patients cannot breathe regularly, so 4D CT often results in breathing sorting artifacts, which significantly degrade biomechanical simulation and property estimation efforts. The fast helical free-breathing CT scans acquired for model-based CT are free from sorting artifacts, acquired over a number of breathing cycles, and deliver relatively low dose. In this study, we present a machine learning approach for automatic lung lobe segmentation in free-breathing CT datasets using a quorum-based constrained generative adversarial network approach and multi-GPU computing setup. Looking at a flowchart describing the data generation and preprocessing workflow, a set of 12 patient datasets was used for training purposes in which each dataset consisted of 25 free-breathing scans. An arbitrarily selected reference scan was semi-automatically segmented using the Pulmonary Toolkit software, where we first generated an initial estimate of the segmentation using PTK's automatic tool and then manually corrected for errors. After verification by an expert, the reference scan was deformably registered to the other 24 free-breathing scans using the DEEDS registration algorithm, with an average mean error of 1.15 millimeters, as previously reported in Du et al. The reference segmentations were then deformed using the deformation vector fields in order to easily and accurately obtain a total of 25 lobe segmentations for each patient. Images were then combined into larger datasets containing all CT scans, which served as source images, and all lobe masks, which served as label images in the machine learning model. Finally, in order to properly format training data for the machine learning algorithm structure, source and label images were cropped and resized in a consistent manner and concatenated. This work utilizes conditional generative adversarial networks, or CGANs, through the Python TensorFlow implementation of the widely cited Pix-to-Pix algorithm. This involves two deep neural networks, namely generator and discriminator networks, and uses an atom optimization algorithm with an initial learning rate of 2 × 10⁻⁴ and momentum term of 0.5. The following equation describes the binary cross-entropy loss function, where n is the number of points, y is the label, and p is the probability of positivity. For each positive or negative instance, log of p or log of 1 minus p is added to the loss respectively. In this study, 12 individual CGANs were trained on separate free-breathing patient datasets for each lung lobe. Therefore, when inferencing for 5 lung lobe segmentations and 12 generator networks per lobe, 60 segmentations are performed in total. In an automatic post-processing step, each voxel was assigned to a lobe of the lung according to a majority-based vote amongst the quorum member networks. And for voxels that were either left unassigned or assigned to more than a single lobe by this criteria, a nearest neighbor search was performed in order to assign lobe placement. On a single GPU, nearly 24 hours of runtime were required to complete a single instance of adversarial learning. For all 12 quorum member networks, for each of the 5 lobes to be trained, 60 networks were trained on a GPU cluster for a total of 1,440 combined hours of computing. During the inferencing process, the model took 0.1 seconds per slice on average to load, and another 0.06 seconds per slice on average to inference. To test the accuracy of lobe segmentations produced by the quorum-based machine learning method versus the ground truth segmentations, 3 similarity metrics were identified. These included structural similarity index, which, unlike traditional image metrics, takes into account texture and structural differences found in the images, where a value of 0 indicates no structural agreement and a value of 1 shows perfect agreement. Normalized cross-correlation coefficient, which is useful in identifying the relative shift between 2 similar-sized images with values ranging from 0 to 1, meaning no shift detected. And dice similarity coefficient, a spatial overlap index, where the value ranges from 0, indicating no overlap, to 1, indicating complete overlap. The average percentage of voxels unassigned or attributed to more than a single lobe during quorum voting were 2.74 and 14.1% for lobes of the left and right lungs, respectively. We found that the resulting segmentations from quorum voting performed equivalently to, or in most cases, improved upon the segmentations obtained from PTK's automatic segmentation feature. The average structural similarity values across test patient datasets for PTK and quorum-generated lobe segmentations was 0.911 and 0.929, respectively. This signifies that the internal structures were highly accurate during both segmentation processes. Average normalized cross-correlation coefficient was calculated to be 0.698 for PTK and 0.806 for quorum-generated segmentations. And finally, the average dice coefficients were 0.696 for PTK and 0.814 for quorum-generated segmentations. Looking at a lobe-wise performance comparison for a representative test dataset, structural similarity index was improved to 0.957 for the quorum approach over PTK's 0.894. Normalized cross-correlation was improved to 0.873 over PTK's 0.561. And dice coefficient was improved to 0.875 over PTK's 0.537. In order to show the benefit of a quorum-based vote approach over the use of a single network, this chart shows the result for each quorum member and each lung lobe for a representative patient. For every metric, the quorum-voted segmentation performed better than any segmentation from a single member network for dice similarity coefficient. To provide a visual component of the quorum-generated segmentations, example slices for each of the 5 lung lobes are shown here. For each lobe, the quorum result is observed to match the ground truth segmentation more closely than its PTK-generated counterpart. Similarly, looking at overlay images of the resulting lobe segmentations and associated CT images, large errors in the PTK segmentation are observed, marked by regions in the yellow circles, while these errors are not present in the corresponding quorum method result, again shown by regions circled in yellow. In conclusion, the proposed quorum-based machine learning approach computed lung lobe segmentations with clinically acceptable accuracy and in near real time using a multi-GPU computing setup. Future work will include testing the inherent scalable nature of this approach by introducing more quorum member networks, member network selection protocols, and testing of different voting techniques and criteria. We also intend to bolster the training data for the outermost anterior and posterior slices, where error was observed to be more dominant. From our own experience, we believe an improved lobe segmentation and fissure identification accuracy can lead to significant improvements in deformable image registration, lung biomechanics estimation, and clinical implementations such as surgical intervention planning and simulation. I'd like to thank my colleagues and collaborators, and each of you for listening. I'd be happy to answer any questions.